Thank you, Mr. Chairman, for the introduction, and thank you to the organizing committee and organizers for inviting me to give this opportunity to give a talk here. And I will describe a little bit about some advanced materials research which I have been doing, but also lately it is more and more important if we would like to create a better world using functional materials, advanced materials, and so on. Then we need to make sure that we at least have some better ways to implement them to the market, commercialization, so they are actually being used. So I will share some of my experiences from my path, from the research, and now I'm more in the utilization, how to create usefulness from the materials, and so on. I will start with sharing my screen. So I will talk a little bit about knowledge sharing, because whatever we do, if we would like to create more usefulness and opportunities and so on, then it's good to share practices, experiences, and so on of knowledge, but also innovation, because this creates more capacity to implement them, to create utilization from the advanced materials and nanotechnology materials. And my background is PVT growth of silicon carbide. So on the left side here, you can see the PVT general principle. So there we have a silicon carbide source, which we heat up, and then it sublimes. And the vapor species are transported to the growing substrate. So I started my PhD studies in the 1990s, and this was a way how to grow the silicon carbide, and it was very many new things in the growth. And the purpose of this is to create a wafer, and on that one, there will be epitaxy and device development and so on. So that was a big hot topic in the 1990s. And in my case, what we did was to, instead of having a long distance between source and the seed, we decreased the temperature. So instead of growing bulk material, we were growing thick layers of silicon carbide. And for that purpose, and the main motivation at that time was the power devices. And then you need thick layers to handle 10,000 volt and so on. And that was possible to achieve thick layers using the sublimation epitaxy. And here you see a graph, a picture of a wafer with an inner circle, which is the epitaxial layer. So that was one of the highlights of my PhD thesis, which I got 1999. So we had nice quality of the material, smooth surfaces, and so on, but they were not useful for the power devices because they were background dopants, which made it not useful to explore the power device application using these thick layers. So that was sort of the highlight of my thesis, a method which was not useful. Then, a few years later, I came into contact with Satoshi Kamiyama from Mayo University. And he had this idea and has started the research about using silicon carbide as a light emitting material. So in that one, we introduce dopants, donors and acceptors. So there's a donor to acceptor pair recombination. And this is a way to get light emitting material with silicon carbide as an active material. So it was a new type of research. So then in that one, there are thick layers needed. And then this method, which we had explored before, became useful again, but for another application. So then it became some utilization. And at that time, we made a technology transfer to make a joint venture to further develop this technology. And that was the time when I came into this, how to make more usefulness from the research and find new ways of commercialization of technologies from the advanced materials. And just as an illustration, how things can create opportunities without planning, like in this case, we had a new research area. In that research area, we started collaboration with Hyan O at Denmark Technical University, and she studies the light conversion and optical properties and how to make a device from this material, which we were growing. And now we actually continue to collaborate since 10 years when we started this collaboration together. And now there are other projects which have emerged thanks to the consortium and the network and the personal exchanges between researchers who are doing things. So now actually in Europe, there's a EU FET Open project on the frequency comb. And in that one, you have one signal, and then one material can split this to many lines. So instead of having like 64 lasers with communication, you can do this in one material or one laser. So this is the frequency comb. So there's a European project on that C-comb. So that emerged into another opportunity of utilization, which were not planned. But let's go back to the nanotechnology background. And all of you have heard about graphene, and you're probably very active in that one. So this is the carbon atom in one layer. And when you have one layer, you have the quantum effects. So the carbon atom, together with the quantum effects, creates a unique amount of properties in this material. For example, it can be used for processors and electronics and so on, but also it has properties that it can be used in composites to be added in other materials. So the application areas are not only one or two, there are many, 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 many. And this is now a big program. And in Europe, you have the graphene flagship. So 1 billion euro will take the research findings to a market. So that is now in running. So that's a big program in Europe, how to facilitate more usefulness from the materials. And I will talk about a little bit graphene on silicon carbide. And in that one, we go back to the wafer, which is grown by the PVT method. And then you grow boules and you cut wafers and polish them, and then you have a substrate for further processing. And in our growth, we have been using high temperature implementation. So for the PVT growth, we do the growth. But for other purposes, we can also heat up the silicon carbide. And when you heat up silicon carbide, you have the silicon and carbon bearing species, and they create vapor species. And then you have silicon, 2 silicon, 1 carbon, 2 carbon, 1 silicon, and so on. And when you heat up this one, then more silicon leaves the surface than carbon. So then you have one layer of carbon on the surface of silicon carbide. And this we started to explore for thin graphitic layers 20 years ago. So there was a researcher who was interested in this graphitization of the silicon carbide, which was not good for the growth. But when we did it intentionally, we could have thin graphitic layers, and they had very high quality. And over the years, then we studied these thick graphitic layers and made them thinner. And in 2005, we had one layer of carbon on silicon carbide. So that was the graphene. But we were not so fully aware what this was good for and so on. But as a grower, we were very interested in that. And then we continued the studies and had a diploma thesis in 2008 and so on. And then 2010, it was demonstrated a very nice result of using this material. So together with other researchers, they presented a quantum resistant standard or results towards a quantum resistant standard using epitaxial graphene. And some important things which are in this context, because it's very tricky to intentionally produce one layer of carbon on the surface. So here you have the vapor pressures. They depend on the temperature. What are the vapor pressures? So that has an influence on the silicon to carbon ratio, how much to have this shift and so on with temperature. And in many materials, you have the steps which are formed, and they can form step bunching, which is not good for the growth. But this is also a way actually to make the graphene on silicon carbide, because you have the bilayers and then the graphene start from the edge and so on. So then the steps are very important. And in the case of silicon carbide, depending on the polytype, you have various bilayers, and then there are several small steps which are merging on that. And the surfaces can look like very different depending on how we have pre-treated the substrate before. So either there are intentionally made steps, or there will be some domains and so on, and different features. In some cases, these are not good for some applications, but sometimes actually these features are useful. For example, on the left side, you have straight steps, and when we have such surface from the beginning, then we can create ribbons of graphene along the steps. So they don't form two-dimensional layers over the whole surface, they are ribbons, and so on. So from a research point of view, this is very exciting. And in silicon carbide, when you do silicon and carbon atom, you can stack them in different ways. You have the hexagonal ones, the 6H silicon carbide, the 4H silicon carbide, but also the cubic silicon carbide, which is very difficult to grow because it's metastable. But they have some different stacking sequences and some difference in properties. So when actually doing graphene on these surfaces, the behavior are different. If we use similar conditions, there will be different behaviors. And sometimes we need to modify the process for a certain polytype and so on. But there are some very interesting features happening just due to the nature of the different polytypes. And this we did in the research. So the leading professor in the graphene in our group, Professor Ruzica Yakimova, and we had many collaborations and more collaborations. And then actually, when we made samples for free for the research, then it became so much interest that we did not know what to do with this. So then we actually started the company. So this became the second inspiration for creating utilization from the research findings. So we were able to sell material, but there is no application which is identified to be a market. So it's very tricky how to go to a market. So that's why this knowledge sharing with the community is so important, because then we can find opportunities in unexpected ways. So that was one of the companies which I was involved in to form. And also we have, for the cubic silicon carbide, we have some smaller samples which have very nice quality. And now we further develop that in another spin-off company to create wafers of cubic silicon carbide. And from growth point of view, I can discuss many hours about how this is formed and what applications and so on. But I would like to use the rest of the time here to discuss the utilization, how to make more usefulness from the research findings. And like in Sweden, it is very difficult to get research funding, and our salaries come from the research fundings. We don't have employment at universities and so on. So we need to find the project money. And now, more and more, we have the needs of the world in order to create this better world using the functional materials, advanced materials. There are various motivations, and nowadays it's very much required that we present related to UN goals, Agenda 2030, where does your research fit? And there are like these 17 goals, but they are very general. So it's not so realistic to say that, yes, we will target this goal number 11, because it's so broad. It's like telling you will go to Europe, but which country will you start with? So then we need other motivations and tools which are along the way. for motivating this utilization, and to share what is happening in Europe, because there are similar programs everywhere in the world to facilitate this. In Europe, the European Commission has launched a guide and encouragement to research and innovation strategies for smart specialization. And this is for the regions to grow. So actually the regions in Europe are asked to find your areas where you're strong, and then you focus a little bit more on those. And then there will be more usefulness. And then they support this because there are some funding ways and so on. So this smart specialization is something which is now coming more and more. But as researchers, we are usually not aware of them because we are so focused on the technology and so on. But I was in the working group in our region, and we have one of the areas, this is advanced materials. So this is why I know a little bit about this and why I'm talking about this utilization instead of the deep physics of the growth and so on, which is maybe more interest for many of the researchers. But there, when we have the regions working, there will be other regions who have expertise. We will find complementary. And when we are sharing knowledge, then we will understand more where our technologies and so on fit in a broader context. And when you have different regions, they will work together in other regions, and then it will be transnational, and then it will be international. Because these technologies which we develop, they have very high impact, like key enabling technologies and so on. But if we are thinking about it, when we motivate our technologies, we present the value chain. We have materials, epitaxy, device, system. And the regions, when they find an area of strength, then they find many actors who are involved in a certain area. And at the end, that is also a value chain. So both the regional development and smart specialization and the technology, they present value chains. But there's not so much overlap, so we can describe these things together. But if we would do this more, then we create more impact because there will be more synergies when we try to promote things to happen. So this is something which is happening in Europe, which the European Commission is pushing for, and it becomes more and more adapted. But it's a slow process because as researchers, we are not aware of these things, and then the communication and information from the region is slow, so it takes some time. But also there are other facilitators similar like this. If we go to the white LED and the blue LED and the Nobel Prize, then you had Akasaki, Amano, and Nakamura who got this thing. So when I heard a talk from Amano at the European MRS conference 2019, then he presented that, yes, we had this white LED technology which started from the research, and it took more than 30 years. And now the funding agencies would like to have more usefulness from the materials and the technologies. But they want it in less than 10 years, which is impossible. So now they need to find a compromise. So the program which they have there is that actually students who would like to become entrepreneurs, they are supported. And those who would like to take the research findings and make them reproducible, so there would be a production, those are encouraged to do that. And for those who would like to make the new technologies, they are also encouraged for the students. And on top of this one, you have mentors, internships, and various ways to facilitate that this happens. So this utilization of the research has a program there. So this was a second example, and I'm pretty sure that there will be various examples from all around the world to facilitate that this happens more. And as researchers, we have to be more aware of them because these are our real motivations when we apply for support to projects. And at the end, it is this exchange which is so important. So it would be nice to be physically there to meet and discuss after the session and in the coffee breaks and so on, because that's when you find real partnerships and new opportunities and so on. So this international organization of conferences, either it's online, that's one way to facilitate that something happens, but also a physical meeting, then you create other opportunities in some ways. And at the end, it's this physical meeting, how to discuss, and when you're curious and visiting labs and so on, which facilitates that this happens more systematically, sort of. So from the advanced materials, the novel findings we are doing towards new or much better technologies, that is a very interesting field. And if we look into the future, because there are climate crisis and all these needs, then this is a way how to create more future sustainability from the advanced materials. And some of the good things in the future, they are developed from the materials today. So hopefully I have given you a flavor of that it is important that we consider the utilization from advanced materials, and we don't need to do it, but we should consider it. If we are not interested ourselves, we can partner together with other people who are interested and create a consortium in those ways also. And this is what I'm now doing more and more. And I had this Almenica as a facilitator, how to create more exchange so there's more usefulness. So with that, I would like to thank you for your attention and hope that this conference will proceed nicely in this combined way of the online and physical meetings, and hope that next time I can come and present physically at this conference. Thank you very much.